everyone. And I think I can see some new faces, which is good. The room is getting smaller and smaller, which is also probably a good thing. So today we're going to cover by example how to go from a program to formulas. So in the last lecture, Ross showed you 4 cool things that you can do if you have an encoding of a program in terms of formulas, right? So you can do verification, you can do synthesis, you can do angelic execution, and you can do debugging. The question that we're going to answer today is how you take a program and turn it into a formula. Today I'm going to show you this on a particular example, which is also going to show up in your homework. And I'm just going to show it on straight line code to figure out how to do this for loops and conditionals. This is your reading for next week. This paper explains how to deal with all the details. The slides are going to be online. Everything that's underlined is actually a link, so you can click on it and get the paper or whatever references we're pointing to. So in the last lecture, we sort of stayed at the user level, right? What does the user see, and what can the user do when he has a solver in the loop in his IDE? Today we're going to go one level below and see what kind of capabilities the solvers offer. What kind of logics, what kind of languages can you use to describe your program or the semantics of your program? In the next lecture, we're going to go down one level below, and Nicholas Ian, who built the mini SAT solver, is going to tell you how modern decision procedures work. So the core algorithm that they use, called CDCL, he's going to describe that in the next lecture. In the lecture after that, we're going to go slightly up to a particular SMT solver which is optimized to work on the kind of finite bounded domains that we usually use in synthesis. So here's the outline for today. First, I'm going to describe the problem, which I'm going to encode by hand for you, and whose encoding you're going to extend for your homework. The first thing that we're going to do is, this is imperative code. It's straight line code, but it is imperative. There are state updates. The first thing that we're going to do is we're going to take this imperative program and turn it into a functional program. As you saw last time, going from a functional program to formulas is pretty easy, right? You can essentially just read off the formulas. This will take us to the part where we actually learn about the input languages of SMT solvers. Today we're going to talk about the theory of arrays, integers, and bit vectors. And I'm going to show you briefly how to use Racket to generate an encoding for this particular problem. Homework 2 is going to be for you to create your own efficient encoding of this problem, plus some twists. And Ross is going to finish up with a 15 to 20 minute presentation on some of the ideas for your semester project, in case you haven't chosen one yet. So, does this sound familiar to anybody? If this sounds too familiar or easy, here are some ways to entertain yourself. Think about using this style of encoding, essentially encoding the operational semantics of a program using different logics. For example, Booleans only. So going directly to SAT without going through an SMT solvers. Bit vectors only, bit vectors with uninterpreted functions, or your favorite logic that may be not even supported by SMT-lib. So if you're bored, think about this. Hopefully you won't be bored though. So here's our problem. What we want to do is we want to transpose a 4x4 matrix. What we're looking at here is a very straightforward executable specification of what it means to transpose a matrix, right? It's trivial. Note here that we're representing this matrix as a single array, right? So we flatten the rows of the matrix. So in order to do the transpose, we're just doing some simple arithmetic here, right? So does everybody agree with me that this will transpose the matrix? Okay, step 0, you should agree with me. All right. This example comes, by the way, from a sketch grad student contest, and you will see what the challenge is. So here's our simple implementation, and it's going to work, but it's probably not going to be very fast, right? So we have these nested loops here, and we're doing multiplication and so on and so forth. To make it a little bit faster, we can actually use SIMD. We can parallelize this using an operation that is provided by the Intel processor called SHAFPS, which stands for Shuffle Parallel Scalars. And this is what the instruction looks like. It takes 3 inputs and produces an output. The inputs are 4 words each, and plus 1 control bit vector. This bit vector consists of 8 bits, which we view as 4 values of 2 bits each. These control how we select what goes into the output vector, right? So the first 2 bits select the first entry of the output from x1, right? So some of these, 0, 1, 2, 3, or 4, we don't know which one. The second one selects the second one, and so on and so forth. Is this clear how the operation works? Right, so the instruction is pretty simple. So how do we use this to parallelize matrix transpose? Well, it's not entirely obvious. So you have to have some high-level insight, and this is the whole point of synthesis and sketching, right? We're not going to automate programming. We're just going to help you do the kind of grungy, uninteresting part. The interesting part that this student came up with is this insight that you could transpose a matrix M using these shuffle instructions in 2 phases. In the first phase, we're going to shuffle the matrix M into an intermediate matrix S using some number of shuffle instructions. We may not know how many. And in the second phase, we're going to reshuffle S into the output matrix T, again using some number of these shuffle instructions. So what does that look like? So here it is. Here's phase 1. Here's our intermediate matrix S, again represented as a flat array. We're using the shuff S instructions. We are selecting 4 words from M for x1 register, 4 words from M again from x2 register, and then we're selecting some of those control bits, right? Some bit vector of size 8. So we don't know how many of these shuffles we need. And phase 2 looks exactly like phase 1, except that our input matrix is going to be the result of the previous phase, and we don't know how many of these shuffles we need. And this is the output. Okay, so far so good. Now, this is what the synthesized code looks like. Note that I replaced this particular thing, unknown number of shuffles, with this repeat operator, which is available in Sketch. It just says choose some number of times to inline the body of this loop and do it. That's the semantics of that operator. And this is what Sketch synthesizes. Yeah?
Sorry, so repeat, you want to change every ShuffPS instruction, you want to change the index in M, right?
Yeah, that's why it's inline as opposed to actually executing the loop, right? So actually this repeat gets expanded into this,
okay.
Right? So it first tried once. If inlining once doesn't work, there's no solution. It does twice, it does 3 times, and so on, right? So it just keeps on going until it finds a solution or runs out of steam. So this kind of, I think, illustrates very nicely the point that I mentioned earlier, which is, synthesis is not going to help you program. I mean, it's not going to write a program for you, right? But it will do the grungy part, right? I mean, think about trying to actually come up with these indices yourself and these bit vectors in order to implement this transpose, right? So this is a parallel implementation of a 4x4 matrix transpose. And if you don't believe me that it's grungy, the person who actually came up with this problem, it was a challenge given to him during his internship, and he spent half a day bit whittling, trying to come up with these constants. And you can synthesize this with Sketch, which is a system developed by Armando Ras, a student who's now at MIT. You can do it in less than 2 minutes, right? And the program that I just showed you, you see with the repeats, like that. Here I'm just implementing the semantics of the shuffle instruction, literally, right? We're just gonna inline that. And when I run sketch, it's gonna take about 2 minutes. So we are going to come back to that. But trust me, when we come back, it will have a solution for us. So there you go, half a day of work versus 2 minutes. And the other thing that we're gonna have for you at the course website after the lecture is a series of transformations of this transpose example, which give more and more and more information to the synthesizer. And when you run it, you'll see that as you give more information to the synthesizer, the synthesis time gets lower and lower and lower, right? The more insight you give it, the faster it solves. So the first piece of insight that we're going to give it, for the purpose of this lecture at least, is we can observe that perhaps, or even guess, if your guess is incorrect, it's no problem, right? If you just run it to the synthesizer, it will tell you no solution, right? So let's say we guess that we just need 4 shuffle instructions per phase. Why 4? Well, it's not an unreasonable guess, right? So it's a 4 by 4 matrix, and we're guessing we need to do a shuffle per row, right? So if we're guessing that much, we might as well take it one step further and just fix the left-hand side. So we're actually not solving for these indices that we're assigning into. We're just saying, okay, in the first phase, I'm going to compute the rows of S, then I'm going to compute the rows of T, and I'm going to do it using these shuffles. Right? So does everybody agree with me that this is the version of the thing that you've seen before, except with some more insight? Right? It's a very straightforward transformation. Okay, so far so good. What we're going to do now is we're going to translate this straight line code into an SMT formula. And we're going to do it in 4 steps. The first thing is we are going to get rid of these funny synthesis constructs that we have, right? So we have this implements construct, we have these question mark thingies, we're going to get rid of those. The second thing that we're going to do, or that we would do if we had any loops, is we would unroll them to obtain a bounded acyclic program. In your reading for next week, you will see how that is done, and you will also see how to handle if-then-else statements. The third step is essentially after the first 2 steps, you will end up with a very simple straight line program, right? Finite bounded straight line program. It will still have side effects though. Side effects are bad, right? We want to get rid of them. And we're going to do that by converting it into SSA form, single static assignment. But this is a special form of single static assignment where we're also doing it for the heap, not just the local variables. And finally, once we're done with that, the formula will be obvious. You can essentially just read it off of the program. Just like in that triangle example that Raz had last week, right, where the formula was basically 1-to-1 with the program, it's going to be 1-to-1 again. Slightly more complicated 1-to-1, but you can definitely see the correspondence. And as I said, we're gonna see how to do it with integers, and your homework will be to do it with bit vectors. And okay, so we're ready to start with step 1. The first thing that we're gonna do is we're gonna get rid of that implements clause. So what does this implement thing says? Well, it's just a correctness condition, right? It's basically saying we're adding this assertion explicitly that the array T that we compute is equal to the transpose of M, where transpose is our functional executable specification, right? Like that very simple doubly nested loop that I showed you before. So we've gotten rid of one synthesis construct. What are we going to do about these question marks? Well, we're going to turn each one of them into a fresh symbolic variable, right? So it's a thing whose value we don't know, and we want to solve for it. And its value is symbolic, it's not concrete. So it's a fresh symbolic variable, right? And here I've given names to these variables to kind of remind you of their role in that shaft PS instruction, right? So this is selecting the X1 register for matrix M, X2 register for matrix M, and this is the IMM selector variable for matrix M. right? So the name should remind you of what's going on in there. Now, we also want to get rid of these bulk array accesses. So if you're familiar with MATLAB, what this means is give me a subarray of this array starting at this index and read off 4 elements of it, right? That's basically what the syntax means. We want to get rid of that by replacing it with a call to an explicit read function. This read function is trivially implemented. You can think of it as just allocating a new array and copying into it values AI, AI plus 1, AI plus 2, and AI plus 3, okay? It's pretty easy, completely straightforward. It just reads off the 4 elements starting at I. So what are we going to do about the writes? Any ideas? So we still have updates, right? We can't really make this into a formula. How do we get rid of updates in general?
Create a new array. Just gonna create a new array.
Exactly. So basically what we're going to do is we're just going to copy the arrays, right? And this is essentially what SSA is. You never assign to the same variable once, right? You just give fresh name to these intermediate values that you're creating. So what we are doing is instead of writing into array, we're calling this write function. And the semantics of this function is it returns a copy of the array that you gave it, except at position I, it copies the 4 elements from the delta array, right? So the 4 things that are different. Okay? So far, so good. And we thread all of these updates through the code. Is this clear? This should be pretty simple, right? Okay, good.
So it's good to point out that at this point it's a functional program, not an imperative program. Everything is assigned once.
Exactly. So we don't have any more updates, right? So this is practically a formula. Depending on what kind of logic you're using, how powerful and expressive your language is, you can essentially just read off a logic formula for this. And we will see that if you're allowed to use the theory of arrays, which we are, or which we will use, there's going to be, for each one of these statements, a very simple formula that pretty much looks like what you're seeing right now, okay? So once this program is functional, as I said, you can turn it into a formula. What kind of formula you turn it into, what kind of operators and data types you use, and which kind of solver you use to solve this formula is going to vastly affect performance. So here are some experiments, very simple ones that we did on a very puny machine, this little MacBook Air that you're looking at. And here are the different encodings and different solvers that we use and the times that we got, right? So here's how you should read these things. QF means quantifier free. So we're not going to use any quantifiers in our encoding. And each of these letters stands for a theory, which is, as we'll see later, the set of data types and operators you're allowed to use. So here it says, if you encode our formula using no quantifiers, and you can use arrays, you can use uninterpreted function, and you can use linear integer arithmetic. And you have choice of 2 solvers who fully support this. Z3 is going to do reasonably well. CVC3 is going to time out after 600 seconds, right? So for each of these logics, as you can see, the timings are vastly different. And we are going to look at the top few logics today. And next Thursday, we're going to look at the relational encoding using Code and our tool Rosette. So we are going to use the Z3 input language. This is a superset of the SMT lib 2.0 standard. The standard should be accepted by most SMT solvers, but there are features which are supported by the standard, and Z3 which make it easy to write formulas that some solvers don't support so well, which is why we're focusing on Z3 and using it for this particular lecture. And in addition to that, Z3 does have some features which are not included in the standard. So for example, as we'll see in this lecture, you can have constant arrays, you can have algebraic data types. So actually, Ross used that in the last lecture. And it also can reason about relations and fixed point constraints. So we go back to this question of what a theory is. So we keep on saying, oh, you know, what is this logic that you are using? What is a theory? For formal and very nice definitions, if you're interested, I recommend that you look at Leonardo Di Mora's SMT tutorial. But informally and in practice, what this means when I say a theory of foo, it means all the formulas that you can write using a particular set of data types and operators that are defined, and these are chosen so as to be efficiently solvable, right? So theory of integers allows you to say, to have the integer data types, to do addition, multiplication, to compare them, so on and so forth, right? So it's just a type with some operators defined over it that you can use for which they are efficient decision procedures.
Linear.
Linear is efficient, yeah.
So you cannot multiply two unknowns, for example.
Yeah, you can, but it might not work very well. Okay, so how are we going to go from our functional program to the theory of integers and arrays? So that's going to be our first step, right? So, so we have these funny symbolic variables here, and the first thing that we're going to do is we're going to encode them as some kind of Z3 variables. So what's the natural thing to do? Well, these things are indices, right? And these things are arrays. So we're going to represent the indices as integer variables, and we're going to represent the arrays as array variables. What a surprise, okay? So what does this look like? Well, one of these holes, mx1 sub j, let's just concentrate on this one. The rest of them are going to look exactly the same. We say that it is an integer variable. You do that by issuing this declare constant command, which is kind of strange. Yes?
I'm sorry, I'll wait until you're done with the slide.
Okay, all right. So this introduces a variable with this name of type integer, okay? This assertion here says that this particular variable is in the range between 0 and 12. And this is how you issue a command to the solver and tell it, here's a formula, I want you to push it onto your stack, right? So at the end, after we've pushed everything we want onto the stack, we're just going to ask it to solve, right? So now comes the question that maybe one of you can give me an answer to is, where does this assertion come from? How did I know to put this in? Why did I do it?
So are you really asking what the compiler would have to do in order to generate this formula? Presumably you don't know anything more than the sort of the source specification and the source sketch.
Yes.
Well, you know the size of the input array is 16. The maximum element the index would be 15 and 4 offsets. So that's what gives you the 12.
Perfect. That is exactly the answer. So a lot of these assertions come from the language semantics, so they're implicit. So you're not going to see this in the source code, right? But it's implicit in the language semantics. In our language, we don't allow array accesses out of bounds. So the compiler, in order to enforce that, is going to have to generate these extra assertions. So here, as Philip said, we know that this has to be between 0 and the length of this matrix M that's being indexed minus 4, because we're reading all 4 elements. The length of the matrix happens to be a constant, so it just simplifies to this. Yes?
So do we have to write these assertions for each of our mx j variables, or there's
Yes.
a macro
No.
by hand? Okay.
Exactly. Well, not quite by hand. You'll see. You'll see on the next slide.
Okay.
You can write it by hand. I would recommend it. It's going to be very painful.
Yeah, I imagine.
So now we're going to encode one of these Mij variables. But here I appear to be doing something really weird, right? So I have one Mij variable, and I've introduced 4 constants. Why? So does anybody remember what was the purpose of Mij in the original coding, right? In that shuffle instruction.
That was the 8-bit vector where you had to take 2 bits at a time.
Exactly.
Index into the
Exactly. How are you going to model an 8-bit vector if you have only integers? You have nothing else.
So you could have it as a complete integer, but I guess it would be simpler to split it up into 4 2-bit integers.
Exactly. And that is precisely what's happening here. And here's the answer, right? So this Mi controls the selection from the read into this output array, and it is a 2-bit value. Therefore, it is in this range. So we introduce 4 variables for each, and we constrain it appropriately. Everybody happy with that? So here's the answer to the question of whether you should be generating these formulas by hand. I don't recommend it. You can use your favorite programming language to generate the formula. It's completely up to you. If in your final project you wish to embed your synthesizer into Racket, the easiest and the best way to learn Racket is to download it and to play with it, to look at some code. The documentation is excellent. So whatever you're seeing here doesn't make any sense right now. If you look at documentation, it's going to be clear. But what I'm going to do is I'm going to just walk you to this particular example and show you what it's actually doing, right? So here, these 3 functions together are generating all of the declarations and assertions for the MXIs and MIs and SIs and so on and so forth, right? Okay. So here I've defined a function. So note, if you're familiar with Haskell, you can see that it allows functions that accept different kinds of inputs. So it's a case split. So it takes in a prefix and a suffix, and it produces a new name, a new symbol separated by an underscore. And here it takes a name and 2 suffixes and does the same thing, right? So that's pretty simple. This thing, it outputs using this pretty display function Racket, which just kind of indents things nicely. This list, which consists of the symbol, declared constant, of the actual value of this variable that was passed in, and the symbol integer. Okay, now this probably doesn't make any sense unless you're familiar with scheme. Who's familiar with scheme? All right, so it makes sense. For those of you who doesn't, this operator here is the uncode operator. So it's basically saying, create me a list. Whenever you see something in here that is not escaped, and the escaped is this comma here, then you just insert the symbol, declare constant, into the list, right? But if you see this escape thing, the thing that comes right after the escape, you should actually pick up its value from the environment, right? So here you will pick up the value of V. You're not going to print the symbol V, right? That's it. And this little thing simply iterates over all the names that we have, MX1, MX2, SX1, and so on and so forth, does the declaration, and same for MIs and SIs. And just to kind of make it a little bit more tangible for those who have not seen Scheme before, here is the code that I've just shown you. And the best way really to understand what these things do is just to use this REPL loop, which is very nice. So for example, we can see how this variable thing behaves. So for example, variable mx1 of 0, what does it do? Well, it outputs the symbol, right? So it creates a string and then it converts it to the symbol separated by underscore, right? Just as I said before. So what does this declare int constant thing do? By the way, this code and the entire file, this actually does the entire encoding that I'm going to go through today, is going to be available online. So you can take it and modify it to do your homework if you want to. So here we have some variable. We'll give it a name v, and let's say that it ranges from 3 to 5. So what does it do? Right? So it's exactly what I said, right? This quote thing, right here, it outputs the symbol, the actual literal declared constant. This v was a bad choice of name here. Maybe we should do something like this, just so you can see it's actually picking up the value from the environment. There you go, right? So it prints that. And the final thing that we have here on the screen, it actually generates all the variables for our encoding like that. So this is the kind of thing that you do not want to generate by hand, right? There it is. So again, it's going to be online. You can use it, abuse it, modify it, and hopefully have an easier time than doing it by hand. So we are now ready to talk about arrays and our array variables, right? So we've seen how to encode our selector variables, the ones that select indices, and now we're going to see how to encode the actual matrices, right? So here what I'm doing is I'm introducing a new variable called m. I'm saying that that variable is type of array from int to int. So the type or sort in the logic lingo, array is parameterized, right? So you have to tell it what kind of things are indices and what kind of things are values. In our case, we're using only integers, so arrays are maps from int to int, right? So this is what the declaration says. In order to do synthesis, we have to give at least one sample input, right? So let's say that we just want to solve it for the array 0 to 15, right? The dumbest input you can possibly imagine. How do we do that? Well, we add some assertions saying that the entries in this array are exactly these values. So this select symbol is a special symbol in the theory of arrays, and what it does is a read. It takes in an array variable and an index. In our case, it's an integer, but it can be anything, right, depending on what you declare up there. And it gives you the value stored at that position. So how do we say that m has 0 at position 0? We just assert that it's equal to 0 at select m0, right? So far, so good? Excellent. So in order to do synthesis, remember we need input-output pairs. So in addition to the input, we need a valid output to which we're going to compare the output that we're going to compute. So what's a valid output? Well, for our particular input, it's just the transpose of this matrix. And I do the same thing as before. I just punch out all the assertions. And the thing that we're using here is a special Z3 thing. This as constant creates an array constant that has values of a particular type at all indices. So we're using the Java semantics, which is when you create an array of integers, it's 0 everywhere, right? So we're saying here that our initial state, the initial state of our intermediate matrix S, is empty, 0 everywhere. Same for the matrix T, right? So when we do the declaration int 16 of T, this is what it means, right? There's nothing in there.
So at this point, it might be useful to say that for this particular problem, we are lucky and a single input is a sufficient specification, sufficient constraint for synthesis.
Mm-hmm.
But in general, we need more, but as long as your values in the input matrix are distinct, and they sufficiently constrain what the transpose needs to be, but they do need to be distinct.
Yes, but by the way, what Raz just said, we know that by reasoning about the problem ourselves, right? For this to actually be proved by the tool, you have to have an inductive synthesizer. And I don't know if Raz talked much about that in the last lecture, but that's what we're going to learn about, how to pick these inputs. We chose this problem specifically so that it has one super input-output pair, such that if you solve it for that pair, you solved it for everything. And in this case, the key property of the super-duper pair is that everything in the input has to be distinct.
So it seems like these examples are really more distinct symbolic variables.
Mm-hmm.
Why are we describing this in terms of the particular example rather than merely saying these are unique elements? Wouldn't that be a more concise way to describe it?
Unique elements of what?
So simply say that rather than assigning every one of the arrays an integer value, name it explicitly as a symbolic integer and say there's an inequality constraint between the various symbolic integers in the array.
So you could certainly do that, but it's going to be much more efficient if it doesn't have to solve for that, right? Because if you do that, you introduce an extra constraints. You're saying, I have this matrix, I don't know what's in it, but I know that the values have to be distinct, so solve it for that kind of matrix. You can certainly do that, but it's much more efficient if you have a concrete input. It's the same game that we're playing all, that we're going to be playing for the rest of the semester, right? The more things you can make concrete, and the more constants that you can give to the solver, essentially, to propagate, the better. So yes, you could certainly do that. Just describe the good input declaratively, but if you can give a concrete pair, that's better.
It's good to point out that not only it would be less efficient, it would require another quantifier, because you would be asking, does there exist these holes such that for all integers that are distinct, the function is correct. So you couldn't even really feed it into a solver.
But you could, but you could do it in two phases, right? You could do an existential quantifier and say, just find me some input such that they're all distinct, and then feed that in.
Just find me all inputs that they are all distinct, but there are many of them.
No, you just say there exists. So it wouldn't solve the synthesis problem, but you wouldn't have to give a particular.
Oh, I see.
Yeah.
I see. So it's also interesting to point out that if you go to the sketch demo, the sketch compiler does not receive from the programmer any such insight.
And the demo should be done by now, I think.
I think so.
Let's see. There it is. Okay, yes, it is done. In fact,
Just want to scroll down.
I guess it's not displaying. It's not happy with the resolution. There we go. Okay, so it is done. It found values for our holes, and it told us that it only took it 40 seconds. It's not bad.
But what is interesting is that the knowledge, sort of a lemma, that one input with distinct values is sufficient. That's your human insight, right? That's
Yes.
a lemma that you proved, well, didn't, but you claim you have on
Mhm.
paper. The sketch synthesizer does not know this lemma, and it doesn't try to discover it or prove it. What it does, it tries to find several such input matrices with different values, and it finds those holes such that on all of these input matrices it is a correct transpose. And then it verifies that it is a correct transpose by asking what I got, is it the correct transpose, or is there an input on which it fails? That's how it obtains all these inputs. So we cannot tell from this demo how many iterations, how many inputs it used, but I suspect way more than one.
Yeah.
How is it verified?
Which lemma are you speaking of specifically here?
the lemma that one carefully chosen input is sufficient to constrain the system in such a way that if your transpose is correct on this input, it is correct on all the other inputs. And that is the lemma, call it a lemma, I'm just being fancy, that the sketch doesn't know, and so it finds enough inputs to get a program that is correct, and then it verifies it. How does it verify it? Well, it poses the verification query that we covered last time. It essentially asks, does there exist an input on which my specification, which is this inefficient code, behaves differently than the program that I synthesized.
Okay, so we have all of our variables defined. So we don't have any more holes. We're now ready to write some functions. This is really exciting. Okay, how are we going to implement that read for instructions that I mentioned? Well, recall the semantics of read for, right? So it takes its input as an array and a position, and it returns a new array of size 4, which simply consists of the elements AI through AI plus 3. So how do we express this in the theory of arrays? Well, we have to introduce one more additional symbol, which is a part of the theory of arrays, which is this store function. Store takes as input an array, an index, and a value. And its semantics is it returns a copy of A, except that at position I, it has this value B, right? That is the semantics of the store formula. Yes.
So it's essentially like an assert, right? Like you can define two arrays and assert that these values are the same except for the particular inputs.
Yes, we can. Yeah, you could, but
It's a good observation.
yeah, but this actually might be more efficient because that way you're explicitly introducing intermediate variables, and here you're not, right? You're actually just constructing terms,
Sure,
so you don't have to introduce more stuff. But you're absolutely right. Yeah. So here, what it's doing is its initial thing into which it's going to store is going to be an empty array, right? All zeros. So it's going to store an element at position 0, whatever it got from AI, right? And it's going to get a new copy. It's going to get a new array. Then into that new array is going to store at position 1 the thing that's at the position I plus 1 in A, and so on and so forth, right? So you can see how this is constructing the thing that we want, which is a new array with this property. And here's the write. It is pretty much analogous to the read. Again, it's a straightforward transliteration of the semantics of this write instruction. We're saying it returns a copy of A, except that at this position I, it replaces the 4 elements with whatever comes from the array, right? So here it is, the name of the instructions, the type of the arguments, and the type of the output. And this is what it looks like, right? So it creates a new array. The first copy of A contains D0 at index I. The second copy of A contains the second copy of this copy contains, and so on and so forth, right? So it's just a little functional cascade that returns copies until you get what you want. Straightforward. The shove PS instruction, again, is just a very straightforward implementation of the semantics. That's it. And here is, as I promised, what one of those statements fully translated looks like. So what we're doing is we are giving a name to this thing as 0, right? So define fun is not introducing any new variables, right? It's like a let. It's giving just a name to this particular expression so we can call it later. And it says that it's a write of S. And what do we write to S? Well, we do this shuffle. The only difference is that this mi0 has been broken up into these 4 integer variables. And all of the remaining ones are translated analogously. So the only thing left to translate is our correctness condition, that the array that we eventually get, which we will call T3, is equal to the actual specification of the transpose, right? M3, the thing that we defined with our assertions. And notice that we're using this equality symbol, we're applying it to two array variables. So when you do this, you're relying implicitly on the so-called extensional theory of arrays. So the solver internally asserts that every two arrays that have all of the same elements at the same positions are equal, right? As it will turn out later on, this is a very nice and succinct way of saying this. It's a handy thing to be able to say, but you may not always want to use it for performance reasons. Yes?
Was there anything we defined earlier that said how big the domain of indices were? Like that is 0 to 15, I guess?
Yes. So the integers in Z3 are true mathematical integers. They're infinite. So that's why we had to add those extra constraints saying that, 0 through 12 for the matrix selected variables and 0 to 3 for the...
But we didn't declare the array sizes. We just put
No,
constraints on them.
there's not even a notion of an array size. The only things that are defined for arrays in Z3 and actually in SMT-lib as well are the two operations that I showed you, store and select, and some solvers, Z3 included, allow you to compare two arrays using equality. Some solvers do not allow you to do this, right?
So because integers are infinite, these arrays need to be
Yes,
infinite.
essentially.
Index them.
Yeah.
So can you show us again where T3 and M2 are actually coming from in the code?
Sure.
Actually, just one quick question.
Yes.
Why are you writing array int? Why do you need two ints?
One is for indices, one is for values. So it's an array. So it's an array. Array is a function, a mapping from ints to ints. So it could be you could have bit vector indices and integer values,
Okay.
bit vector indices and bit vector values. So you have to tell it. It cannot infer that on its own. So its type system is not very sophisticated.
I think this array is being mapped, is what I see in the other languages.
Yeah.
Yeah, that's pretty much what it is. That's pretty much what it is.
So this is a little bit off topic, but we're getting all of these cases where very minor changes in the encoding have big performance impacts. This is reminding me a lot of parallels with optimizing compilers. Is there such a thing as a optimizer for your specification to sort of get rid of the stupid stuff so you don't have to worry about it?
This would be a fantastic project.
When you invent one, let me know.
You'll get really
You'll get
famous.
very, very famous and very, very rich.
And I want you to get famous in this course.
But the answer is that there are some tricks that you can play. And in fact, SMT solvers, which are so-called eager SMT solvers, which don't actually do any reasoning about logics by knowing something about the axioms of the logic, but they essentially translate everything to SAT. So they will do simplifications like what you're talking about, but that helps only to a certain extent, because at the end of the day, you're doing search and you're relying on CDCL, right? And you're doing learning, and there are all sorts of heuristics. Basically, small things like reordering, the way in which you declared your variables can make your problem, run anywhere from 2 seconds to 20 minutes, right? So, there's like no way to protect yourself. The best thing you can do if you get stuck is randomize. Either change the random seed or permute the encoding of your formula, and I'm not even kidding.
So in a sense, these solvers are intelligent, not quite like humans, but intelligent, and you get the same response with humans. You ask them and somebody can give you the answer, somebody gives you a wrong answer.
Yes, pretty much.
You then leave this, you enter the fragile state.
Yeah. So the answer is, to some extent, you can prevent yourself from doing very stupid things, but even if you're very smart, you will get stuck. And back to Matt's question about where the variables came from. So I think think. Here it is, right? So the empty one is the output of this transpose thing, so it's the spec. When we gave it our input array 0 through 15, so it was a transpose of that.
Okay.
S0, well, S, the initial S is this thing, this initialized to 0, right? Which is why we made that constant array. And all the other ones, like the defined fun ones, are these the result of this SSA transformation,
Okay.
right? So here's the T3 is essentially this intermediate update from this right to the T array.
And trans is the slow handwritten
Uh-huh.
version we have from the start.
Yeah. I promised you 3 theories today, right? So we have arrays and integers, and I'm going to show you some, just a very basic way of declaring bit vectors. It's going to be your job to figure out the details and how to take this SIMD encoding from the integer one that we'll make available for you and convert it into bit vectors. But here's a little bit more new syntax that you're going to see. So this defined sort thing simply introduces a new name that refers to this sort of bit vectors of length 2. Notice that the length of the bit vector is important. Its type, it's part of its type. So you cannot add together a bit vector of length 2 and a bit vector of length 3. It's not going to type check, right? Yeah.
Why is underbanded?
Hmm?
Is underbanded?
Well, I have no idea. It's just part of the syntax. Honestly, I really don't know. I'm sure there is some reason. Yeah, that's just basically what you write, and that's how you say that something is of type bit vectors of size 2 or bit vectors of size 4. So you can, so whenever you see these things, you can just inline this expression, but it's just nicer to give it a name so you don't have to do it.
This is just the equivalent of a type dash.
Yeah, that's all it is. Yeah, there's nothing special here, it's just name substitution macro.
Might it be a parameterized type def? Is that the case? Could you
It
provide
is.
a variable type?
It is. So you can actually do fancier things for bit vectors because the sort doesn't take any parameters. You just do it like this with the empty parentheses. So the thing that we're going to change, we are now going to make our whole bit vectors. Remember, they used to be integers. They're now going to become bit vectors. So declare const part is the same. So now it's a bit vector of size 4. It used to be an integer. And we still have to give it the range bound, right? Because bit vector of size 4 can represent things outside of the range 0 to 12, right? So we still have to give it the explicit constraint that our variable is greater than or equal to 0 and less than or equal to 12. And here's another piece of bizarre syntax. This is how you declare a bit vector constant of size 0, which has length 4, bit vector constant of size 12, sorry, of value 12, which has size 4. Okay? Just a bit of weird syntax. These, again, you can find in the documentation, but they are bit vector equivalents of less than or equal to, right? So you'll have these little weird names for the corresponding integer operations.
So to check, there's a fixed mapping between values and bit vector representations here. How would you represent something where you wanted to use bit vectors like an enum or something, where you want to assign different values to? Maybe I should ask you that first.
Okay, I'm not sure I understand the first. You can ask me afterwards. Okay, so we're left with the holes. Again, the clear constant is the same, except that now we are actually using 2-bit values to represent our 2-bit values. I mean, isn't that satisfying? What's even more satisfying about this is that we don't even have to write the assertions anymore, right? So bit vectors are unsigned by default. So when you have bit vector of 2, of size 2, you can only represent values 0, 1, 2, 3, right? So I don't have to add those extra assertions saying that mi00 is in that range.
Does this make any performance difference at all?
We haven't run the experiment. Knowing how the decision procedure works, yes, it should make a difference. We have not run the experiment, so I cannot say definitively.
Which way would you expect it to make a difference? Would you expect the bit vectors to be faster or the arrays or the integers to be faster?
Well, can we take a vote? Who votes for integers? Oh wow, we have only one integer guy. Really? No one else? No one else? Wow, okay. Well, bit vectors are faster in this case. And in fact, so the question that one might ask, which is, I guess, a variant of the question that you just asked, is why bother with this bit vector thing, right? I mean, if you have mathematical integers, they're really nice, right? You can write whatever you want. You don't have to worry about any ugly details, modular arithmetic wrapping, so on and so forth. So why would you use bit vectors? Any ideas?
So you mentioned that if you use bit vector, you don't have to do those assertions,
Mm-hmm.
and that get rid of like a lot of assertions.
That is one reason.
So they're bounded. If you want to deal with, the solver deals with bounded things, it's obviously going to be faster.
Exactly. So the two reasons are essentially what you both said, which is when you are actually reasoning about machine operations, well, machine operations are bit vector operations, right? They're not real mathematical integers. So you can precisely model them using bit vectors. And the decision procedure that we use for reasoning about bit vectors is different than the one that we use for reasoning about linear integer arithmetic. Depending on the problem, it can be much faster. Normally, this is done by what we call bit blasting, which is converting all of these bit vector operations into circuits, which are then handed off to a stat solver to solve. And that can be a lot faster. And this also explains why it's important to set these bounds as tightly as possible, right? So if you can get away with using 2 bits, don't use 4. Because remember, it all gets down to SAT, and with SAT, the more bits you have, the more variables you have, the larger the search space. So you want to restrict the search space. Smaller the better. And this brings us to your homework. Actually, I was going to say our homework, but I'm on this side. Your homework. Part 1 is I've shown you how to do the encoding of straight line SIMD transpose using integers and arrays, and I've shown you the beginning of how to do it with bit vectors. Your job is going to complete the bit vector encoding. You will have these slides, of course, and you will have all the code that I've shown you so far. So you will have the generator, and you can generate the Z3 formula yourself and run it and see how long it takes. It takes about 2 minutes on my laptop. If you have a faster machine, it should be it might be a bit faster for you. But the encoding that you come up with that uses bit vectors should be significantly faster. So I was seeing 5x. Maybe you can get better than that. And the hint here is don't rely on that extensional axiom if you want it to get really fast. Another hint is you will see that if you read the SMT lib tutorial, there is an option called set logic that you put at the beginning of your encoding, which tells the solver which theories you're using. Tell it which theory you're using. It might be faster, right? So that's another hint. Part 2.
I didn't get the first hint. Can you just repeat that?
So the first part, remember how I had a term in my encoding that compared 2 arrays with the equality operator? Try not to do that. It might give you a performance benefit. Part 2 is create an encoding of SIMD transpose where you have unknowns both on the left-hand side and the right-hand side, right? I showed you what to do only when you have holes on the right-hand side. I want you to do it with the holes on the left-hand side as well, and if you go to slide 11, you will see what I mean, right? So it was like one step before the encoding that I translated. And if all of this sounds really trivial and easy, you should come and become our PhD student. But anyway, here are some things that you can do to keep you busy and procrastinating on your thesis work. Try scaling your encoding to larger matrices. Try 8 by 8, 16 by 16, see how far you get. This is actually a real world problem that people care about because figuring out these bit vector constants by hand to do these parallel computation is very, very painful, especially when you have large matrices. Try a different solver. So far, we've seen how to generate this encoding for Z3. Not all solvers support as rich a set of theories as Z3 does, but they may perform better. So if you go back and you look at the table that we had, you will see that in this particular example, we actually got STP to perform better than Z3. So see if you can use a different solver. And finally, what you can do is, if you're feeling really crazy, is you can try an encoding that does not correspond to the operational semantics of this. And if you want to know what that means, you can talk to me after class, and Ross is gonna tell you now about some ideas for the semester project in case you haven't come up with anything yet.
I'd like to go to the sketch demo and point out one thing that is actually relevant. So we have been talking about how adding more insight, just a little bit, can gradually improve solver performance. Why is this important? Because in your projects you may get into a situation where you want to synthesize something extremely ambitious. Ambitious to the point that it would all beautifully work if only the solver actually terminated on time. Okay? And so here I want to show you one example of one trick that you can play, because you will probably have to play other tricks. This should not come across as disadvantage. You should view it as benefit. If it doesn't scale, just give it a little bit of more hint. So can you describe in English what I've done?
You eliminated a hole. So there were two holes, one for the repeat, one each for the two repeats. Now you're using the same number of steps for each one. So instead of forming all, Cartesian pairs from 1 to 4, 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, it's now just going to try 1, 2, 3, 4.
Right. In fact, the Cartesian product here was bigger. I believe that by default, these holes have 5 bits in Sketch. So that was quite a bit larger combination. So in terms of English, I now entered very easily this additional hypothesis, which says, well, I don't know how many steps I need, but I know that both of these phases require the same number of steps. And the beauty is that in this language, at least this particular hypothesis can be entered very easily. And if we run it now, it should be just a few seconds, and it was 9 seconds in this case. So it's sort of on the order of 5 to 10, 12, depending on what random numbers it chooses. So remember such things, and remember that this is part of the advantage of using partial programs, because often these additional knowledge can be entered as an assertion or as a program shape, and it helps the solver quite a bit. Now, you can see here that we still have these unknowns here on the left-hand side here. If we replace them with constants, then presumably it would run even faster, but we didn't try it.
It does. I actually have 4 encodings I can download them and try it.
I see, for Sketch.
Yes.
I see, okay. So you can also, when creating your encoding, you can also try it in Sketch in this language, compare your performance with what this backend does. You can also change the program in such a way that it doesn't iterate over all inputs, but you give it this one particular input from the lemma, the one which has distinct inputs, and then it will only do the synthesis on this one. And so that's all I wanted to say here.